Okay. So this is the last section that will be included in the exam. Okay, the first exam. So it's section 4.3, a fundamental theorem, or evaluating definite integral. Okay, evaluating definite integral. Okay, so here is what we are going to do. So there is one theorem. So let's write it, and yeah, we will prove it also, because the proof is very simple, and you have all the tools to follow it, which is a good thing. Okay, so let's do that. Here is the theorem. Okay, theorem says that if we have a continuous function, let's f is continuous on closed interval EB. Okay, then so if we have function, then the definite integral which we interpreted as an area. Okay, when f is positive, so it's exactly the meaning of the usual area we know. So it's exactly is the difference of capital F at B, taken at B, minus capital F at E, where capital F is an antiderivative, is any antiderivative. We know that if we have one antiderivative, we can add any constant, and we have then an infinite function of the antiderivative. Is an antiderivative, okay, derivative of small f. Okay, so this is the main theorem. It's very simple, you see. So let's prove it. So we'll ask you. Okay. So let's see, have a look at the proof. It's very simple. You will see it's a good one. So uh, we will because here we remember we defined the definite integral, the area, using Riemann sums. We used the subdivision of the interval, etc. So let's start from here, because we will use the fact this quantity is the limit of Riemann sums. So trying to come to this quantity, to show this quantity. Okay, so consider a subdivision. So let's okay, x0 equal a, x1 equals so x0 plus delta x, etc. Let's say xi equal x0 plus I delta x until you reach xn equal b, with delta b a subdivision, b a regular subdivision of the interval EB. Regular subdivision of EB. Okay, with delta x regular, we said it's just it takes the length of the size of the interval divided by n. Okay, so that all yes, the size of all the subintervals are equal to delta x. Then consider let f. So f, capital F is an antiderivative of f. Okay, so f an antiderivative of f. Then let's write this difference. So we start from this difference. If we form the difference, we are hoping to reach this equality. So fp minus fe. So what we will, so it's exactly f of xn minus f at x0 with there's notations, okay? We did nothing here. Then here, look what we will do. We will add the term and subtract the term and add it, so that we don't modify the starting code, the original expression, okay? So xn minus 1. Then I add fxn minus 1. So of course they thought about it. So here I'm just giving the idea how they did it. Okay. So it's not evident to think about it. Okay. But once we learn proofs like that, then they become like when you solve exercises, some recipes, there's also become, we can think about them because they are repeated in many proofs then. Yes, the last one will be fx1 minus fx0. Okay. Okay, then what we did here, so this sum, so we can write it as using sigma sums. Okay, so sorry, the sigma sum. So I will, you see this term, is cancelled by this one. This one will be cancelled the following one, etc. Fx1 will, there is minus fx1 behind it. So I didn't change my expression. I wrote it differently because it will help me. So I can say it's the fxi minus fxi minus 1 starting I. So like I am now focusing on those differences. Okay, I'm adding all those differences. Okay, I will be from 1 to n. Okay, so let's check. If you start 1, you have fx0, fx1, the last term. If you end at n, fxn minus fxn minus 1. So we did well. Okay, so we are adding these differences. Now let's take these differences. Now, um, here we will use something. We want to use something here. Remember that capital F is, since it's an antiderivative of F, we have, so we have a capital F prime equal F. This is the meaning of an antiderivative. Okay, that means capital F is differentiable. Okay, capital F is differentiable on the interval AB. Okay, since and yes, what else? It is continuous. We need the continuity also. Yes, F is continuous on the interval EB, because we have also F is continuous, so F prime is more regular. Okay, F prime also is regular. Okay, is a continuous. Is continuous. So capital F is differentiable and continuous on EB. So I am saying that it is true. So inside there is no problem. Between open interval differentiability is stronger. Now we have continuity also at the endpoint of capital F. Okay, I will think about this one. Why at E and B? Okay, why at E and B? Why I need these two assumptions? Because I want to use the mean value theorem. The mean value theorem says the difference between two endpoints. Okay, on a um, on a closed interval xi minus 1, I can say that the difference is the derivative of capital F at an intermediate point, let's call it xi star, times the difference of the two values, xi minus 1. So here we applied from the mean, if you remember, mean value theorem, applied to F, capital F, on, we will apply it on each interval xi minus 1 xi, okay, on each interval. Now we will rewrite these quantity. First, we know that we have, first we note that xi minus 1 is just delta x. Okay. Now, what is f prime? F prime at xi star. It's just because f prime is f, it is just f xi star. Okay. Then let's come back to our this expression fb minus this difference fa. We said it's the sigma, the sum I to 1 of this difference, but this difference is an fxi star, fxi star. This difference is an fxi star times delta x. Okay. So this is what, yes, then you can take both the limit to both sides. If you take the limit fb minus a, okay, as n approaches infinity, is the limit. We know this quantity is finite because it's number fb minus fe. F is capital F is continuous. Yes, I think there is something that shows F, capital F is continuous, or we will see it later, I think. So it's continuous, okay? Or I think it's an antiderivative of continuous function is continuous function, but there is a way to see it later when we will see another theorem, okay? Uh, okay, so this limit is number, you have, so it's constant function, so the limit is this constant itself. The other side, you take the limit. So we are sure that the limit exists because it's equal to this sum. This sum, and this sum, if you remember, it's exactly Riemann sums. Okay, delta x, the xi star is inside. Okay, and xi star, we know it's inside the interval xi minus 1 xi. Okay, and since it's a Riemann sum, we recognize it. So, and our function is continuous. We know that from one of the theorems we said any continuous function has a definite integral. So this one is exactly the EB. We were wanted to show the x. And this limit is exactly the value of b minus fa. Okay. So you see the proof is yes, is helpful here. We see the application again of the mean value theorem. Okay, how it is important for proving other results. Okay, we said when we studied it last semester, it's not the importance of the theorem. It's not itself, but more all the theorems, the results we establish using it, like the monotony, the concavity, and now look at the connection with a definite integral and the antiderivatives. Okay, so finally now, as long as you can find an antiderivative of your function, you can compute the exact area under a curve given by y equal fx over an interval AB. Just take the value of your antiderivative at endpoints, the highest endpoint, minus the value of the antiderivative at the other endpoint, and you have your area. So there is one remark here why it doesn't depend on the constant we are adding to an antiderivative. So for example, so let's put it as a remark just to see it. Remark here. Okay. So suppose that you have, yes, suppose that F1, you have G, another antiderivative. G so will be necessarily an F plus C. Okay, G is G. G is another antiderivative. Derivative of F. Okay. Okay. So you now. So if you want to compute the area from E to B, fx dx. Okay, we established that since with f, it's f capital F B minus f capital F A. Now, if g is another derivative, so g, I see it is f plus c. So the difference will be constant between them. So you can express g or f as g minus c. Okay, so you will have g minus c, okay, at b minus g minus c at a, taken at a. Now you take, so you have the function g at b, the constant function, you apply it at any point, it's the same constant, minus g at a, and the constant function applied at any constant is the constant. Okay, so you have this. So it is true that it doesn't depend on which antiderivative you take, because there's constants, they will cancel anyway. Okay, so it's enough to have just one, you choose one antiderivative and you compute your area. Is it clear? The meaning, do you see is it clear? The formula? Yeah. Okay, let's do an example. So simple direct application. For example, what is the area? Compute the area 0 to 1, x square dx. Okay. So last time you remember with Riemann sum, we had the sum of 1 over n, this n squares, etc. We added term for it was long. Okay, it wasn't okay. So the theorem says as long I can find an antiderivative of x2, then I can. So what is do you know an antiderivative of x2? What is an antiderivative of x2? So we said it's the function that when we derive it, we will get x2. What is it? The function when you derive it, it gives you x2. What is it? You remember?
X3.
Yes, x3 over 3. Okay. When you derive, you get x2 plus a constant. Okay. So this is my capital Fx. I decide, okay, let's say Fx. Or just I will choose this one. The constant is not important for me. I will choose one of the, one of, that is simple one, okay? So I will say, so it will be, let's say f at 1, okay, minus f at 0. So it will be 1 over 3 plus c, if you want to work like that, will be 0 plus c. And you simplify, you get exactly 1 over 3. Okay, so our area under the curve, the parabola on the interval 0, 1, 0, 1. So the image is 1, 1 here. So and 0 is here, and you have your parabola. So this area, this part under the curve, so its value is 1 over 3. Okay. Okay. So there is a notation, it's a practical notation. Instead of using each time referring to f, we take a constant or not, we can use this notation fx dx, okay, or writing fb minus fa. We write fx is not, we refer to an derivative of f, and we will take it between x equal a and x equal b, which means exactly when you write something like that, means fb, you will take the function at the value b minus, so the highest here, the endpoint, minus to the lower endpoint, okay, fa. So we use often, it's practical. Look, for example, 0 to 1 of x2 dx. I will say, I will choose just one without the constant. I will eliminate the constant. So x3 over 3, I know the antiderivative of the function, and I will take it between 1 and 0. It's better to specify if you want an x here. But yes, for the moment, there is no confusion. I don't think it's necessary. So you can take, or just to remember that you need to take x equal 1. So you will have 1 over 3 minus 0 over 3, which is 1 over 3. Okay, instead of using f, etc. Yes, in one side you can say, here is my antiderivative. Okay, you found it, general. Then you take just one of them, you put it here, and compute to use the consider the endpoints. Okay, so you can use this notation. Yes. Yes, another example here. For example, what about the integral from minus 2, 1, x3? Okay. So what is I need to know antiderivative of x3. So do you remember? Yes.
X squared over
Yes. x4
x4.
over 4 plus a constant. Okay. Then I need just to take one of the, the antiderivative. So let's take this one. And I will take the value endpoints minus 2 to x equal 1. So I will substitute the value of x at by 1. So 1 over 4 minus, so I will have minus 2 power 4 over 4. So here, if I compute, so I can simplify 1 over 4. I will have 4, I can simplify, and minus 4. So it will be 1 minus 16 over 4, which is minus 15 over 4. Okay. So this is the area. So remember here why it is negative, because if you graph your function here, so let's do it here. If we graph the function, so x3, we know the shape, the global shape of x3. So 1, 1. For minus 2, you will have minus 8. So it's very far, the point is very far down, okay? Minus, so, and we know how it was to minus 1, 1, let's say. So we have something, the global shape of our curve. Now we are working between minus 2 and 1. So the area, if you look at it here, so you will have, remember, where is the region here that represents this number? So if I want to color it here, so it will be my, from minus 2 to 0. So remember the subdivision is here on the x-axis, okay? And then you take a point and take the value, read the value, the height, you consider the bars. Remember, Riemann sum. So what I'm computing here, I'm computing this area, okay? And when I am here, the subdivision, and when I read the points, the value, the height of the bars will be in this direction, not down. So the area will be this one. So when you compute this quantity, it will be a negative number because your sum is negative. And then here it's positive, but the quantity of negative numbers is more larger than this one in absolute value. So that's why we get something negative. Okay. So when my function is always positive, then we have the usual area, meaning of area. So we are expecting a positive number. But when your function is behaving like that, can take negative values. So consider it as a generalization of the definition. That's all. Okay. Using Riemann sum. Last time we introduced the other notation of antiderivatives like that, so we don't have to introduce it again, but we can use it here also, since we introduced the antiderivative of f like that, which is my capital Fx. You can say I will take an antiderivative between the function that I will obtain between a and b. Okay, you can use this notation also. Okay, so let's put it here. Okay, so yes, this is there's many things you need to know. Yes, so for this chapter, yes, this is what you need to know. Notation, how to evaluate area or definite integral using an antiderivative of the function you are integrating. Okay, so it's the value of the antiderivative, the difference of the values at the endpoints of the interval. Okay, then the notation, there's different notations. Just you should be able to use any one of them. Okay, you use them and understand the notations anywhere when you see them. Any question? Any question about that? So this part is included in the exam. Okay. So the next, what we'll do next time, so it will not be included for. Yes, so even we study it, it's not included. So practice on this one and the Riemann sums and properties of integration, algebraic operation on computing areas, etc. Okay, so let's practice then. So we don't have it. Let's practice. First example here. So find the area. So compute the area or find the area of under the cosine function. Cosine function on the interval 0 pi over 2. Okay, so we are asked to find this one. Then yes, let's do this one. We will do other one. Yes, we will practice. That's all. We will do more practice than. Okay, so let's start slowly. So how can you interpret here? How can you answer the question? What you are asked to compute an area under the function and on the interval. So what will be your answer?
Est-ce
Alors,
qu'on
just
utilise l'intégrale?
oui, oui. Donc on va utiliser l'intégrale de quoi?
Cosine x.
Cosine x. And yes. Donc c'est une aire. It's an area. So you need to specify.
Square.
Sorry.
Um,
So when you compute an area, you need to specify you start from from where to where you're under your function. Okay. So what do you need? This is if this notation is an antiderivative. Okay. This one, if I leave it like that, this one is a function antiderivative. Can you give me the antiderivative? Antiderivative of f. Antiderivative of the function fx equal cosine x. Okay, this is what we learned. So be careful. The notations are very clear. So this is a function. Okay, so let's compute the antiderivative anyway. We'll need it. Okay, an antiderivative of cosine x. We said we look for the function that I derive and get cosine x. Which function, when I derive it, it gives me cosine x. Yes. Yes.
Sine x.
Yes, sine x, any plus any constant. So we have an antiderivative. Okay, now, so you see it's a function depending on x. Okay, so this is a function. It's not a number. It's not an area. Okay, it's different from an area. Area is just a number. You measure something and you have the number. Okay, so there is a difference between this notation and the notation from E to B. So we make the difference exactly. Okay, this one is a number that expresses an area. Let's say if my anyway, it's an area positive or negative in the large sense. Okay, so it's an area. Okay, but which area? It's the area we express. We said this notation is practical. Why? Because it gives the function, it specifies the function, the endpoints. Okay, you have the endpoints. Okay, and here you have also the variable. It says which variable we are using. Okay, so it's the area under, we said under y equal fx. Okay, between and between or over the interval, the interval eb. Okay, that's why this notation is important. Okay, so instead it's sin x dx. Okay. Oh, it's not good. It's not. I will write it. Okay, integral e to b of cosine x dx. Okay, so you have here x is the variable, the function, you have the endpoints, and what you have here is an area under the function, the given function. This is your function fx, okay, over the interval eb. Okay, while this notation gives you just an antiderivative, which is a function. It's not an area. Okay. Okay, we found sine x. Okay. So since we are specifying exactly what is the area, how can you express here the area of the cosine function on the interval 0 pi over 2? So which number? What is your area? How can you write it? As formula, which formula you will use? Yes. Which formula? Is it? Yes, you can try. Just it's better to make the mistakes here. So what do you think? I want the area under the cosine function on this interval. So it should be what? How can I write it, express it? Yes.
Would it be sine of pi over 2 minus sine of 0?
Yeah. So this is your calculation. Yes, it's correct because you used the theorem. Okay. But before giving the answer here, what would be your formula using integral sine the symbol integral? How will you write it? The area.
Integral of sine.
Sorry.
Is it the integral of
Uh-huh.
um sine x with 0 at the top and p over 2
Zero.
at the bottom?
Uh-huh. And sine x like that.
Yeah.
Is it this is the function they told you, the
Of
area
course,
and cosine,
sine.
okay? Yes. So it's cosine, okay? It's cosine x, okay? So this is the area. They are asking you to write this. Okay. Now, using the theorem we established today, we said that this quantity is exactly will be. I can compute it if I know an antiderivative. So let's. I'm doing the same mistake. So I need the antiderivative of cosine. Okay. Once I found the antiderivative, I will take it between the two values. Okay. Antiderivative of cosine, we found it, it's sine. Okay, let's take just one of them, which is, I take it between 0 and pi over 2. And then, yes, we substitute the value, the upper one first, sine pi over 2 minus sine 0. And we get, yes, 1 minus 0. Okay, so this, yes, so between these sentence, you need just to interpret right the definite integral, then find your an antiderivative for your function and take the difference of the values. That's all. So this is the yes. And now you see, finally, it seems we don't have anymore this problem of Riemann sums. We are happy now. We need just an antiderivative, okay, and we can compute these areas, okay. But the difficulty then is to find. Yes, it seems it is easy because you are substituting to value to function. If you have a formula, you substitute and you make a difference and you get your area, which is easy. We can do it. So, but the difficulty, of course, is how to find an antiderivative of the function of any function. So we will learn for most of the part of the course. We will focus on two. We will develop two techniques. The first one, I think, we will see it next time, and then we will stop for a while. We will introduce new functions. So one chapter just adding the exponential function, sine, the inverse for trigonometric functions, hyperbola, logarithm. So we will add more. We will add to our library more functions. We said functions are important for modelization, so we are adding new ones. Once a way to add one, for example, the logarithmic function, we will see using integration. Okay. Once we did that, we will learn another method, integration by parts, and we will apply it to these different functions combined, and we can like that be able to have more possibilities computing antiderivatives. Okay, but still there exist functions that we don't know their antiderivative. Like I said, the exponential minus x2, we don't know an antiderivative. Okay, it's not known up to now today. They didn't find an antiderivative of this function. Okay, they were able to compute, for example, um, I don't remember exactly the endpoints, okay, A and B of this function, if you remember, involves in statistics. We are able to compute, and the graph, if you remember, it's the Bell function, okay, something like that. So if you adjust here the endpoint, so the area here over R, of course, it will be 1. If we had, maybe there is a factor that we have to adjust here. Although, but the computation of the number is done differently. Okay, it's not through finding an antiderivative. Okay, by another method. Yes, so this is how why it is important. So to know how to compute antiderivatives, because it solved many situations. Okay, many problems. Okay, so let's do now. So I'll give you and try. You have to do. Okay, even you do mistakes, it's better to do them here. and see why, yes, so you correct your understanding, and okay, it's not, this is the purpose, okay? Otherwise, you can read. Book. Okay, so what about, let's go slowly. We said 0 to 3 under the function x3 minus 6x dx. So let's, you tell me how, what I do, or if you are able to write, you can write also directly. What do you think? So the idea now, find an antiderivative. We will not use Riemann anymore. It's not, we cannot compute this, make this subdivision and form the sums. We don't know always the sums, okay? This partial sums and take their limits. So we will use the theorem we saw today. Okay, I think it is called fundamental theorem 1. There will be a second one. Okay. So what will be my antiderivative? Can you have it directly without doing through calculation? And then I will take the values between here. Can you guess an antiderivative? Well, we can also do it here separately because it's new also, antiderivatives. Everything is new, but it's easy. You can just practice, okay? Okay, so let's do it here in parallel. What about an antiderivative of x3 minus 6x dx?
Is it
How, yes, how can you do it? Just the steps, exact. Go slowly.
is it the antiderivative of x3 minus
Yeah,
antiderivative
exactly.
of 6x?
Exactly. Minus 6 times an antiderivative of x. Yes. Yes, exactly. This is what we will do. Yes. And then these are, we know antiderivative in this form because it's power. Okay. So what will be an antiderivative of x3? So can you remind me
Um,
xn in general,
X1.
antiderivative of xn? Do you remember?
uh, so let me check.
Yes, check. It's new. At the beginning, you can't for,
Is
but
is
yeah,
it x
yeah,
n plus 1 over n plus 1
exactly, exactly. This is, yes, plus a constant.
plus c?
Okay. Yes, plus a constant. So this is, yes, something you, by the end of the semester, you will have a list of antiderivatives. It will be big, larger, you will see. So yeah, yes, it's at the end of the book, usually you have a page for this antiderivative. So keep it in front of you always. So yes, this one. So each time I see a power, I think about this one. So we will say x, it will be x power. Yes.
3 plus 1,
3 plus 1, exactly, over
3 plus
3
1.
plus 1. Okay. We don't need to add c. We will add it. We will add just one c at the end because all, okay, we said that, okay, minus 6. Then for this one will be x. What is the power here? Do you see it?
1 plus 1.
Yes, exactly. 1 plus 1 over 1 plus 1. Yes, do it slowly until it becomes a habit for you. Okay, so it's, now you can simplify, of course, x4 over 4 minus 6 x2 over 2 plus a constant. Okay, so now I know my antiderivative. I come back here, right? Take only 1 over 4. 6 over 2 is 3 minus 3 x2. And here are my endpoints. Then I substitute. Okay, substituting means you take this quantity, you substitute 3 first. You, okay, the highest, the upper end. Okay, so you will have 3 power 4 over 4 minus 3 times 3 power 2. Okay, minus. Then open, don't forget the brackets so that you don't do mistakes. So 0. So here it's 0 power 4 over 4 minus 3 times 0 square. Okay, so these quantities is 0. Here, so you have these, you can factor, for example, you have 3 power 3 as a factor. You can put it outside 3 over 4, then minus 1. Then you have 3 minus 4, it's minus 1. So you will have minus 3 power 3 is 27 over 4. And this is your value or area. Okay, so this is the way. And for a moment, you know only this one. You know, you are supposed just to know the x will be the function you need cosine minus cosine, because the derivative of cosine is minus sine with minus plus, so you get your function. And you know the other one is what is it was cosine, yes, cosine x dx. We said it's sine x. Okay, that's a constant. When for a constant k, it's the same. It is included here. It's k times integral of 1. 1, you can write it x0 dx. Okay, so it will be k times x0. You have x0 plus 1. It's x. Okay, so you will have x kx plus a constant. Okay. Okay. So yes, that's all. So these are the only one you know for a moment. We don't know more than that. Okay, you don't know more than that. So it's easy to keep. And always you bring yourself to something like that. And we said it can be fraction, so you can include also fractions here, which is good. Okay, let's do one more. So what about this one? Integral from 0 to 12 of x minus 12 sine x dx. So we are looking for an area. We know we use the fundamental theorems saying that it will be an antiderivative taken between the 2 points. Okay, so I need to find this antiderivative. So what do you think? How can you find an antiderivative of this function? Yes, yes. Steps, yes, go slowly, but at the same time you are reviewing the antiderivatives, and then you are applying it for computing areas. So at the same time you are doing review. So how will you approach the problem? Look, find the antiderivative. How will you do it?
First we can find the
Sorry?
do
Hmm?
we
I
can find
didn't.
the antiderivative of x minus 12 sine x
Antiderivative of x, yes, minus
minus
12.
12
Antiderivative of,
sine x
okay. Then what about the antiderivative of x?
x squared over 2
Exactly, x squared over 2 minus 12 times, what is the antiderivative of sine?
minus cos
Minus cosine, okay, minus cosine. And always we said we will add all this small constant here and we put them inside. That's all. One is enough. So finally I have my antiderivative, okay, plus 12 cosine x. That's all. So I will take the value first, substitute. So beginning, do it slowly because it's new. We can do easily mistakes. So cosine of 12, okay, minus 0 square over 2, you see brackets here, plus 12 cosine 0. So here 144 over 2 will be 72 plus 12 cosine 12. I keep it like that. It's a number. 0 is 0. Here cosine 0 is 1. Okay. But if you don't know it, just keep cosine 0. Okay. And you have then minus 12. Here is your value. Okay. Okay. Yes, I didn't finish. 72, I can subtract, we'll get 60 plus 12 cosine 12. Okay. Okay. Yes. So let's do one more. What about this one? And let's keep also, we separate here so that we can do the antiderivatives one side. Okay. What about the, okay, this infinite integral. 0, sorry, not 0, it's 1. So from 1 to 3 of this function 2t square plus t square square root of t and minus 1 and everything over t square dt. So you see your function here is well defined. T, it's not defined at 0, but 0 is not in this interval. So which is good. So we know that, yes, it has an antiderivative, and also this integral is finite. Now, we said, yes, we will use its continuous function over the interval 1, 3. So I can use the fundamental theorem that says it's enough to put my antiderivative here and take the values 1 to t equals 3. So you see, even your calculations are dependent. So you need to not make mistakes on the antiderivative. So let's look for the antiderivative. What is an antiderivative of t2 square plus t square square root of t minus 1 over t square? Okay. So it doesn't seem we have a something simple like square root xn. Okay, but but since they gave it to you, you are supposed to be able to do it. Okay, that means you need just to work on your expression and bring yourself to something you are able to do. So how can you work? Sometimes we need to work on the expression. Okay. Mhm.
Please, can we do the
Sorry.
derivative of this term?
Sorry.
Can we simplify?
Yes. So what will be? Yes. How? What your fraction? Yes. How can you write it?
I did like antiderivative of 2t square over t square
2t square over t square. Yes.
plus antiderivative of t square square root t over
Mhm.
t square
Yes. And minus 1
minus
1 over t square. Okay. Great. Yes.
mm,
dt. Let's simplify. Okay. T square over t square. It's 1. Okay. So we will have 2. T square over t square. So the remaining term is square root t minus 1 over t square. Yes, which is good. Yes, we are. What do you? Yes. What can you work more?
mm,
Do you see it as power? But you have a sum difference. You see, you can do that also. You can say it's 2 times 1, okay, plus square, this step, you can always do it, okay? Like that, you have 3. Yes, you separate. So what about the first one? Okay, what is antiderivative of 1? Dx dt.
X plus C.
You said x. Now the variable is t, so you will use t.
T plus
T plus c. Yes, great, correct. Because you have here 1, you can see it as t power 0. Okay, so this is that connects you to this antiderivative. What about the antiderivative of square root of t? Can you see? Can you write it differently? Maybe it will help. Yes.
Is X to the power of 3/2 over 3/2.
Yes. So here, write it first before finding the antiderivative. Write it as power because it will help. We see it. Then finally, I will use this formula. Okay. It's better to know. Yes. And 1 over 2 plus 1, 1 over 2 plus 1 plus a constant. Okay. So it's t power 3 over 2. And here you have 3 over 2 and plus a constant, which you can write 2 over 3 t power 3 over 2 plus a constant. What about the last one? 1 over t square. Can you bring yourself to powers? Can you write it as power like?
T to the minus 2.
Yes. So this formula, as long as n different from -1, is you can apply it. Okay. So we will have t minus 2 dt, and now yes, t minus 2 plus 1 over minus 2 plus 1 plus a constant. So it will be t minus 1 over minus 1 plus a constant, which is minus 1 over t. What's constant? You see? Then you come back here and write your antiderivative here. So it will be, we said 2t without adding the c. So it will be, let's say c1, c2, c3. We group them all and we put a capital C, that's all. Okay. So 2t square root of t, we found this one, this quantity 2 over 3, t power 3 over 2. And for this one, we have minus minus of minus 1 over t. So it will be plus 1 over t plus a constant. Okay. Then you come back here, you write your antiderivative, one of them, t3 over 2 plus 1 of t over t. And then you substitute. You will have 2 times 3 plus 2 over 3, 3 power 3 over 2 plus 1 over 3 minus 2 plus 2 over 3 plus 1. Okay, so here you have then 2 times 3 is 6 minus 3 it's 3. Let's keep this one like that. 3 power 3 over 2. What else here? Plus 1 over 3 minus 2 over 3 will be minus 1 over 3. Okay, here I have, what is it? 3 power 3 over 2. That is 1 over 2 power 3. So it is, but you don't have to, you can leave it like that. Okay. So I can say it's power 2, then 3, and leave this one. Okay, so that I have a 3 here. so that I can simplify it. So I will have 3 plus 2 square root of 3 minus 1 over 3. You can simplify 9 minus 8, 8 over 3 plus 2 square root of 3. Here it is, your area. Okay. So this is, yeah, it takes many steps, but if you be careful and write things slowly, it's yes, it's feasible. You can do it. Okay. So what about now? Any question for a moment? Any question? So we started this chapter of area. We started it by the antiderivative. Then we introduced Riemann sums, operations on area, algebraic operations. And then today we introduced this yes, fundamental theorem. Connecting Riemann sums, limit of Riemann sums, which is the area, with antiderivative, using antiderivative for computing areas. Okay. So let's think about this question. So here is a question here. What is the problem? What is the problem with the equation, with equality? Okay, equality. There is a problem somewhere. See, maybe there isn't. Figure minus 1 to 3, 1 over x squared dx equal x minus 1 over minus 1, and I will take it between minus 1 and 3, so which is equal minus 4 over 3. So think about it. Look if there is a problem with this calculation. Check. Okay. Okay. So what about the antiderivative? Is it good? Is it correct? Let's check together. What about the antiderivative? An antiderivative of 1 over x2. Is it correct? Or we can look for it. So what? How will we proceed to find the antiderivative of 1 over x2? Yes.
Put it to the power of -2.
Exactly. X negative 2. So its power function, it's different from minus 1. So it will be x minus 2 plus 1 over minus 2 plus 1, also constant. So I will get x minus 1 over minus 1 plus a constant. So it seems it's correct. They took one antiderivative and they put the two values. So if we take, if we substitute, if you take this function, minus 1, so it will be 1 over minus 1 over x, and you want to take it, for example, at x equals 3. So you will get the value minus 1 over 3. If you take it at x equal minus 1, you will get minus 1 over minus 1, which is 1. Then if you do the difference, meaning minus 1 over 3 minus 1, we will get minus 1 minus 3 over 3, which is minus 4 over 3. So it seems correct. What do you think? Is it correct? So this difference is correct. This value is taken as the function correct. And antiderivative is correct. And it seems they applied the theorem and everything is working. Is it? So let's graph this function and see, because we know 1 over x2, we know the shape, remember? It's basic function, and we know how to graph these functions now. Yes, it passes through 1, 1. It's an even function. As 0 approaches, so it goes to infinity. As x goes to infinity, 0 is decreasing function, it's that. We know how to study it, okay? It's symmetric. It's like that. And we are computing an area. Let's say we are from 1, yes, let's say 1 is here, minus 1. And let's 1, 2, and 3, here is the area, okay? So if you look at in terms of, so my curve is above the x-axis. So the meaning of the definite integral is exactly in area. And now look what we have here. So we will have, okay, so what we have, look, you have this and you have this. And it seems positive, and here it's something negative. Where is the problem? What do you think?
The function is not continuous between.
Exactly. It's not defined, okay? The function x1 or x2 is not defined, okay? Is not defined at 0, and 0 belongs to the interval of integration they give us, okay? So the theorem is true for continuous function on these closed interval, but it's not the case here, okay? So we cannot apply the theorem, okay? We cannot apply the theorem, okay? So it's not valid, okay? That's why what we did here, even the calculations separately are correct, but we cannot say this number is exactly this. It's not true. Even here, where there is another concept we introduce, it's improper integral, because your function has discontinuity here, so it's something else, okay? So this is why we cannot do it. So the assumption continuity of your function on the closed interval is important, okay? So yeah, just to be careful, I think. Let's come back now using geometry. So here it's yes, you need to use something so that you will see what you need. Compute the area. So the question is to compute the area of the region. They are describing a region of the region, then region, okay? Under the curve, under the curve with equation y equal to x minus x2, and above the x-axis, and above the x-axis. Okay. So yes, they are asking us to compute an area. So what do you think? they gave you a function and they are asking an area, but they didn't give you something. What is missing here?
The endpoints.
Yes, the endpoints, E and B, which A and B I will choose to have to compute this area. Okay, so but they give some information. The region is under the curve and above the x-axis. So maybe I need to graph this function, and maybe I will have then an idea what is the limits of my curve. Okay, and maybe I will be able to identify the corresponding interval. Okay, so this kind of questions, so you need to do something like that. Now we wouldn't. Since this one we can deduce it from the standard parabola just by completing the square, we will do like that. Okay, so let's graph it. So we will say it's minus x2 plus 2x. We complete the square, remember? Completing the square, so you have x2 minus 2x. Okay, so I have a beginning of square, so it's x minus 1 square. If you develop, you get x2 minus 2 times x, which is here. Then you have plus 1, but I don't have it, so, or maybe you cannot see it, but I will explain. I will do it differently, but I prefer differently. So I need to complete the square. I need just to add here 1. And of course, I need to subtract it because I don't have it in my expression. And like that, I have my square. Here I have x minus 1 square and minus 1. And finally, yes, it's 1. Sorry, 1. It will be 1 minus x minus 1 square. Okay, so we will use just or geometric transformations. You remember shifting the curve to the right, to the left, vertically, or down, horizontal, vertical translation, or upward or downward. Okay, so this is how we will do it, so that we can identify our. So if I try, so normally I have the basic one, basic curve. So the basic curve is parabola. This one, here it is. Okay, remember. So this is y equal x2. Now to get x minus 1, I need to shift to translate my, I need, so the translation, horizontal translation. So I will have something here. Okay, so we will have 1. That's 0. So this is y equal x2. Now I am graphing y equal x minus 1 square. Okay, I'm doing that, this one. Okay, so at x equal 1, the vertex will move here. At 0, I will have these 2 points. At 2, I will have the point here. So my curve will be this one. Okay, so horizontal translation to the right. Then I have minus 1, minus as factor. So the opposite of this graph, of this function has a graph. I can obtain it by reflection. Okay, so here it is. I will have it like that. Or I can do it on the same graph. So let's do it on the same graph here. Okay, with another color. So I will have, it is shifted, so it will be just symmetric with the x-axis. Okay, we will have something like that. Okay, remember this. Otherwise, you can also graph it, study the function and graph it. And then this graph, then we add plus 1. So we move upward by one unit. If I move it, look what happens now. My graph is this one. Sorry, it's like that. So I am here at 1. The vertex for the blue one is here. I move it to by 1 unit, so I will be here. These points will move here by one unit. And yes, the global shape doesn't change. It's just a translation. Okay. So here is my graph. So this is my graph y equal minus x2 plus 2x. Okay. This is what the graph. And the question they said, compute the area of the region under the curve, and above the x-axis. So this is the region they are describing, this one. Okay. So what do you think now? The area, how can you express it using integral, definite integral? Yes. Using the symbol integral, how will you describe your area? Yes. Go ahead. It's better to make mistakes here. Just yeah, just express yourself so that you identify the wrong understanding or clarify anything. You see, this is the purpose. What do you think?
To find the endpoints, we would have to find the x-intercepts, right?
Yes, yes. So let's find the x-intercepts. So they are solution of y equals 0. Okay, y 2x minus x2 equals 0. Okay, so here the expression, we can factor it. Okay, so we have 2 minus x equals 0. So this will happen if you have x equals 0 or x equals 2, which is these are, we are saying here 0 and 2. Okay, yes, this one is important. Now, how can you express your area? When we introduced it, we started introducing the problem of computing an area under a curve. This is what we had, something like that. Okay, and our objectives was to compute this number. So this number, how we denoted it, this area? What was it? Which notation we use it to express the area? Yes,
The integral.
yes, integral. It's the integral. Yes,
B is the upper part and A is
B
the
is the upper. Yes, E is the lower. And of what?
the function.
Of the function. And this writing, just to say, describe all these things. I'm computing an area under the curve given by the equation y equal fx from A to B, from x equal A to x equal B, above the x-axis. This is what it means. Okay. If your function, of course, is above the x-axis, if it's down also, we can understand it down also. Okay. But between x equal A and x equal B. Okay. So let's apply it here. So my area now, how can you express it? You have the function. Do you have the endpoint? Did you find the endpoint?
Yes, the endpoints are 2 and 0.
Yes, they are 0 and 2. So it's 0, from 0 up to 2. The function, what is my function?
negative x squared plus 2x.
Exactly, plus 2x. This is my function. Okay. Now I expressed what I'm looking for. I was able now to find the limit of my interval. I know my function. It's above on this. Yes, I can compute the area. Now the second step, yes, we will use the theorem that allows us to compute this area. Okay, so we need an antiderivative of minus x2 plus 2x. Okay, so because we know from the fundamental theorem, it will be an antiderivative that I will take between 0 and x equal 2. So what will be my antiderivative of this one? An antiderivative, let's work on it here separately. It's new. It's normal that you hesitate. For example, here, what was your hesitation here when you looked at your graph? Is it because it comes down? It's not going up like that? Okay, maybe you are hesitating. It ends just here. It's, yeah. Okay, but don't forget how we approached this area using bars, okay? Adding the areas of the bars. Okay, so what is an antiderivative of this function? This one is easy. So it will be minus an antiderivative of x2 plus 2 times an antiderivative of x, okay? And each of those are power functions, so I can say it's x3 over 3 plus 2x2 over 2 plus a constant. Then you come back here and substitute. Plus x2, that's all. Then yes, you have minus 8 over 3 plus 4, and at 0, this quantity is 0, okay? So you have 12 minus 8, which is 4 over 3, okay? Yes, so yeah, to compute your area, you need to know all those elements, the endpoints, your function, that's all. So yeah, here the information was hidden. So you needed to know, yes, where it falls to see exactly what is happening. Okay. So let's do one, for two more. Look at this one, this question. What if you were asked to compute this one? 1 to 4 square root of 5 over x dx. So here it's clear, they give you everything. Normally you don't, you will have to deal with functions that are regular. You don't need to check, but in case, depending on the question, but most of the time we will work just with the regular functions, okay? Yes, so what do you think about this one? No, normally now you are supposed to be able to find all the antiderivatives because you don't have many formulas. You have only one, then plus the one of cosine, the sine, that's all, 3. But later you will need the book in front of you. Plenty. Yeah, you cannot remember them, yeah. So what do you think? How will you do that?
Can we do square root of 5 over square root of x and then pull out the square root of 5 as a constant?
Yes. So you want to separate like that, okay?
Yeah.
Then you want, so the square root of 5 is constant. You want to put it outside or you keep it inside?
Can we put it outside or?
Yes, we can. We said that antiderivative of k times the function is k times the antiderivative of f. So this is what we are doing here. So it's good to review this. Yeah. Yes. So we are now. What about square root of x? What will you do? Can you write it differently?
Would be x to the power minus minus half.
Yes, minus half. Now it's easy. It's just square root of x minus 1 over 2 plus 1 over minus 1 over 2 plus 1 plus a constant. So which is square root of 5. Here you have x 1 over 2. Here, or 1 over 2, so you can have it here 2 plus a constant. So finally, your antiderivative here is the function 2 square root of 5 square root of x, okay, x power 1 over 2, and take the difference between these two values. So I will have 2 square root of 5. I will have square root 4 minus square root of 1. 4 square root of 4 is 2. Square root of 1 is 1. So 2 minus 1 is 1. So it will be 2 square root of 5. You see? So just, yeah. So let's do one more. Now we will, yes, let's do one more different, like what about the definite integral 0 to 2 of the absolute value of 2x minus 1 dx. Now you have, yes, an area, but with a function that has an absolute value. Okay, so how will you, so you see now we, since we started, we saw just one formula, which is very clear and simple. Okay, just to you need to see where is the difficulty. It's not in this theorem. We understand it through even the proof was clear. You see, easy, and it's clear. Yeah, I need just to find antiderivatives and compute the values, and that's all. But then when we start doing questions, so at the beginning, let's say this kind, we identified the pattern. So we need just to identify the power and have an antiderivative. But then when we change questions like we combine functions, or when yes, we write in them differently. So if you didn't see it before how to approach a question like that, you can spend a lot of time, you see. So that's why you need to discover our different situations. For example, this question, so you need to see it, to see the difficulty. And for this one, for example, so the difficulty is no more in the problem, in the theorem, but the steps how to bring yourself to apply the theorem. And these are, of course, techniques, strategies of solving problems. It's another kind of difficulty. We learn it by practice. Okay. Yes, each function now behaves something so like that. Now we are able, each time we see square root, we think about the power. We bring ourselves to power. It's easy then, you see, because we did it and we saw it repeating. Then we are thinking about it. Similarly, the other situation, now we have absolute value. So what we will do for absolute value? What do you think? Once you understand it, you see it how to do it in category, then you can repeat it. Yeah. Yes. So what do you think about the absolute value? It's always a problem, absolute value, because we cannot, it's not direct formula. It's here with these bars. It changes, the expression changes depending where we are. But yes, we need just to write things, yes, clearly, step by step. So what do you think? We need to open this absolute values. Okay, first thing, just to see what is happening here. Okay, so let's do that. absolute value of 2x minus 1. I use, I remind myself, capital X will be, remember, X if your quantity is positive, and the opposite if my quantity is negative. Okay, so I do the same here. It will be then my quantity, which is 2x minus 1, if my quantity is positive. So just write it, okay? And the opposite, step by step, okay? So you see, already you have two expressions, different expressions. Now, what here I need to, because I'm working with x, I'm locating x here. My x is between 0 2. So I can't keep my expression inequality like that. I need to see exactly where is my x. So I will have this expression 2x minus 1 if, so I can isolate, it's an equation degree 1, move the constant 1, then divide by 2 if your x is greater or equal 1 over 2. Okay, it's the opposite, 2x minus 1, if you have your x less than 1 over 2. So now we know what is the general formula for our absolute value. So now how can you work with this information here? Okay, okay, because we didn't learn an antiderivative of absolute value. We don't know that. We know just the power. And here I see power. Yeah, I know how to compute an integral here of power, which is good. Okay. Now just what do you think? What will you do here so that you know? You know how you have your formula depending on your interval here. So we have an interval here. We have the value 1 over 2. Okay, you have the value 1 over 2. So we have the formula here, 2x minus 1 with x's here, and here you have the opposite. So what do you think? Now your x here for the interval you are working on is 0 to 2. You are working here.
Do we break up the interval between, so 0 to 1/2 and 1/2 to 2?
Exactly. So you can do that for any function. You can separate by a number to 2. Okay. And now for us, it was necessary because we have an absolute value, and this endpoint 1 over 2 gives us the right formula we use on the interval. So for example, when you work from 0 to 1 over 2, your expression will be, if you open this, you remove this absolute value, you need to write that you have the formula minus 2x minus 1. Okay, and when you are here from 1 over 2 to 2, you know that yes, over 1 over 2 you have the formula 2x minus 1, 1 over 2 to 2 dx. Okay, and now it's yeah, so we are almost done because here I know an antiderivative. I can find an antiderivative. So an antiderivative here, you have what is my antiderivative, and I need to take it between 0 and x equal 1 over 2. Here also I need an antiderivative of my function, and I take it between 1 over 2 and 2. Okay, so here I have, we can do it here. Let's erase this part here. I can erase this part, okay? So we have then, yes, an antiderivative of minus 2x plus 1. Okay, minus 2x plus 1. Okay, what is an antiderivative? Minus 2x plus 1. Yes, it's simple. Yes. So you have a sum. If you are hesitating, you have a factor, just go through the steps. Minus 2, I can do that. I can separate 1, the yes, and now it's much clearer. Power. So it will be minus 2 x squared over 2 plus x. This is x0, so it will be x plus a constant. Okay, so I have my antiderivative. It will be minus x2 plus x. Now, the antiderivative of 2x minus 1 dx. Similarly, I will have 2 an antiderivative of x minus an antiderivative of 1. So it will be 2x2 over 2 minus x plus a constant. So I will put here x2 minus x. Okay, then you take just the values at these endpoints. Okay, you substitute, you will get so at 0 it's 0, at 1 over 2 you have minus 1 over 4 plus 1 over 2 plus here you have 2 power 2, it's 4 minus 2, then minus 1 over 4 minus 1 over 2. Okay, yes, so you have 2 half, so you have here half. Okay, so we have half plus half, so it's plus 1. We have minus 1 over 4 minus, it's minus 1 over 2. So 3 minus 1 over 2, 6 minus 1, 5 over 2. Okay, so this is how you each situations, yes, you approach it, but you know what you are looking for, an antiderivative. Now the difficulty is related here to the absolute value. We needed to work on it first. Then, since with the interval is the yes, it includes the point where the formula is changing. We needed to separate the interval into 2 parts. So it can the logic comes. Yes, just to try to explore the situations, because to do it for the first time just like that, it's not evident. You need to work on it first. Okay, any question? Okay, so if you have a question. Yes, other questions on your Maple if you didn't finish, or your assignments also. So normally you have just one more quiz or 3. Normally you can you will be able to do it. And practice. You have 1 week more to practice on antiderivatives, on functional several value partial derivatives, etc. So. Yes, if you have, yeah, I can stop. I think recording.